Bismillahirrahmanirrahim. Assalamualaikum and good day, everybody. So, hope you're in a great state of mind. So, let us continue with the following section. Right. So, previously we have covered the kinetic models for growth. The first one is the Malthusian model, right, and followed by the logistic model, or known as Verhulst's model. And now we come to the third growth model, which is probably the most popular one, known as monod model, right? So for this model, it's called substrate dependent growth model. Yeah, I think from the name itself, you can probably predict that this model will take into account the element of substrate dependent, right? In previous model, logistic models, basically there is awareness to actually add the element of environmental constraints, right? Which could include everything, right? Toxic, substrate, space, etc. But for monod, we specifically add the element of substrate dependent, only substrate, yeah? So during growth and decline phases of batch culture, the specific growth rate is dependent on the concentrations of many nutrients in the medium, right? This is very clear. The growth is surely depending on the level of nutrients or substrate in the medium, okay? But in many cases, a single substrate exerts a dominant influence on the specific growth rate, right? The key word here is a single substrate, okay? And this component is known as growth limiting substrate, right? So for growth limiting substrate, it can be carbon or nitrogen source, can be some oxygen, can be oxidant such as nitrate, right? So usually we deal with carbon, right, as the growth limiting substrate. Yeah, please take note, there is also there probably many substrates in the broth or the media, but for monod, we only take single substrate, okay? All right, and then during balanced growth, specific growth rate is related to the concentration of growth limiting substrate by the monod equation. So basically, monod equation give you a relationship between a specific growth rate, which is mu, and also S, which refers to substrate concentration. Okay, so let's look at the model. So this is the model, all right? Yeah, maybe at first you need to like memorize it, but after you understand the concept, it's not really difficult to really remember this, right? So I think you know this relationship. Mu is equal to Rx divided with X, or originally it was Rx equal to mu X. Remember from the Malthusian? From the Malthusian, the rate of growth is proportional with the cell concentrations. So it is Rx equal to mu X. So you just transfer the X here. Why you do like this? Because you want to make this mu as a function. All right. Okay, this is basically a relationship for the Malthusian, right? But for monod, it now turns to this. Okay, so you can actually remove this if you want. All right. So the mu is equal to mu max multiplied with S divided with this Ks and S as the denominator. So this basically means the mu no longer equal to mu max, right? Let's see if you have an equation of mu equal to mu max, that is for the which model? That is for Malthusian model, right? The autocatalytic reaction, right? So mu is equal to mu max. But now for monod, this element is being added, right? So mu no longer equal to mu max only, but now they incorporated the term S here and also Ks, all right? So in this case, for monod, if the question is, what are the kinetic parameters? The answer will be mu max and Ks. Both are kinetic parameters. And Ks refers to monod saturation constant gram per liter. Okay. All right. Okay. So this is a general curve for that, wherein you have a relationship of first order region and zero order region. You remember this, right? During biophysical chemistry. In the second part of the course, you have been introduced with this first order, second order, and zero order, right? So for this, if you try to plot a relationship between a mu and also the S concentration, the Ks is equal to the half mu max, okay? All right, and the maximum mu is known as mu max, okay? Why mu max? Why Ks is equal to half mu max? All right, we can explain it through this relationship. Okay, the first one, based on this concept, when the substrate S concentration is nearing zero, all right, the equation will be like this, all right? So in other words, you can replace the S with zero, nearing zero, but not really zero. So meaning the mu max will be times 0 point something, 0.00 something, Ks plus S. This S also will be like 0.0 something, but then since the value of S is too small compared to Ks, this is a mathematical concept, right? I think we have learned this before in biophysical chemistry as well, wherein you have you remember the initial reactant concentration, C minus X is equal to C because the X is too small. So it's the same with this. You know, when you have the S is too small compared with Ks, maybe here 10 to the power of -7, here is 10 to the power of -4. This one is too small. So it could be neglected. But here you can't really neglect at this fraction because it still gives you a value, and that value will significantly influence the reading here. And therefore, the equation, if when the S is nearing zero, you get a mu equal to mu max times S divided with Ks, right? I hope it is clear. So it generally means that when the S is too small or nearing zero, but not exactly equal to zero, only the substrate in the denominator is cancelled out, right? Denominator at this region, this S is being removed out. Now we move to the second part. When the S is nearing to infinity, meaning we have abundance of substrate, no limitation, you see, the equation will be like this equation, mu equal to mu max S divided by Ks plus S will now be equal to mu equal to mu max, to behave like the Malthusian model. Why? All right. Imagine this is a very big value. All right. This S is very big value. Okay. And this S also very big value. When this S is very big value, you can't ignore it. This one retain. But then this one, the big S, if this one is become very big, this Ks can be neglected because this value is too big. It's the opposite like in the first case, all right? So you got like mu max, this S and S can be cancelled off. So that's explain why mu equal to mu max, all right? And then the third one, when the S or the substrate concentration is equal to the monod saturation constant, this is basically in the unit of concentration as well. Let's say if the S is equal to Ks, right? You just replace this with Ks, this one as well, right? So the equation will be mu equal to mu max divided with 2. And that explains why Ks is equal to mu max divided with 2. Meaning, if you want to determine what is the Ks value, it is actually half of the mu max. All right, is the concentration of substrate at the half of mu max. You can determine by extrapolation or just based on calculation. Okay, so this is monod model. And the derivation of this is actually based on the Michaelis-Menten model. Is actually similar. All right. Limitation to monod model. I think previously you can you can realize that we talk about single substrate component, isn't it? So that is actually the limitation. The application is limited to single substrate only. You have only one S, right? Existence of long lag phase and acceleration phase of batch culture. So in a growth curve, right, there is also phases known as lag phase and acceleration phases at these phases. And we know that at these phases, although we have abundance of substrate, but then the growth is still very slow, right? The rate is also very low. The growth rate also very low. So this real case scenario does not really being represented in the monod model, right? Because monod model will just be correct for true or true for all other phases beside the lag and acceleration phases, right? Because in the real world scenario, you have a lot of substrate. The cell still takes quite a long time to grow, right? Quite some time to grow. So, but the monod model does not really represent this region. Okay, so that is basically one of the limitation. All right. So similarly, for every model, we talk about the Malthusian model, then we talk about the logistic model, right? I think, yeah, for Malthusian, there's also the linear model, right? Or graphical model. Why you have graphical model? The graphical model is for you to draw a curve, let's say a linear curve. You can draw a curve with the model of y equal to mx plus c, and then from that you can determine the values of the constants based on the slope and also the y-intercept, right? So it's the same for monod. There is also the graphical model. For monographical model, there are several types, all right? So the one that I'd like to introduce here is called Lineweaver-Burk plot. It is a two-guy name, all right? And then this is another one, Eddie-Hofstee. So for Lineweaver-Burk plot, it will be equal to this, all right? In which, if you look at this, if you draw a curve of y, this one is a y, 1 over mu, as a function of 1 over s, right? The slope will be equal to Ks divided with mu max, while the y-intercept will be equal to 1 over mu max. Okay, so while Eddie-Hofstee, this is the new arrangement, all right? So this one is mu here actually. It's the same with mu, right? This is mu, specific growth rate. This one also the same. Okay, it's a mu actually, refer to mu. They are basically the same, they're interchangeable with the Michaelis-Menten one, mu, this symbol, and also this mu symbol. Okay, so for this, can you identify the y and x function? Right? It's easy. Usually the one with kinetic model is the one that you want to determine. This is mu max. This is kinetic parameters. You're going to determine this, right? And then clearly it's not going to be your y or x axis. And for this one, this is a kinetic parameters which you usually determine through experiment, right? And then this is the substrate. You can have this in from your experimental data, and this is a kinetic parameters, which is actually Ks. This Km is from Michaelis-Menten, so they are basically the same. So it's the same with Ks, right? So if you need to determine the kinetic parameters for mu max, one system only give you one value of mu max, right? And if you need also to determine this Km, this Km is Michaelis-Menten constant, but if you relate to monod, it's actually the Ks. It's the same, right? So this is also kinetic parameters. And if you want to determine this, you basically need to plot this as y and mu over s as the x axis. Okay. But yeah, the question is, do you think you have to memorize this and this, right? It's actually simple, right? You may not need to memorize this, but you should just understand how they derive this equation, right? There's two guys here involved, right? For Line-Weaver-Berg, basically how they do it, they just use this arrangement, taking the reciprocal of this, and then you can generate this, all right? And then here we go. You have this Line-Weaver-Berg. So yeah, it's quite puzzling when you have two two names, two researchers or two scientists just to come up with these equations, right? So another one is the Eddie-Hofstee one. For this one is a bit challenging. What they do is they invert and multiply with mu max. All right, then they rearrange it, and then they take the mu as a function. So I expect everyone to try this, and I believe you can try to rearrange it and come up with this. And right, you don't have to really memorize. Okay. As a note here, as I mentioned, this v mu function is the same. This one is for Michaelis-Menten, while this one is for the monod constant. They are basically the same. Okay. All right. So this one is for the your assignment. You can I want you to find out how you can derive this form of the graphical model for monod equations. All right, just a rearrangement. Okay, and this model is called Haynes-Wolff plot. All right, so meaning that if you have a monod equation, this one, all right, in your fermentation data system, the question is usually what are the values of the mu max or Ks in your system, right? So you can determine your mu max and Ks using graphical model with a plot of a linear model y equal to mx plus c. But then the values of these two are depending on the type of graphical model that you use. You have Line-Weaver-Berg, you have Eddie-Hofstee, and you have another one, Haynes-Wolff here, and the values are usually different. And you need to state which models you use. Usually people just do more than one models, or maybe three, just to show the values. All right, and then with these values, you can compare with previous research or previous references to study the performance of your fermentations. All right. For example, this is the Ks value. All right. This is value of Ks. Okay. Ks value for certain species and also the substrate. This is what they take note that the unit of Ks is the concentration, right? Is the concentration of substrate when you have half of the mu max, right? So these are the values usually in the literature. So what's the point of having all this is that when you run your own fermentation, you can compare with this Ks. And then you can just compare, I mean, in terms of whether it's lower or higher than your Ks, and whether if you are using the same strain and also the same type of substrate, are you getting a similar Ks or not? Is it better or lower? So you can obtain that kind of relationship and also comparison, all right? Oh, next, we have rate of cell death. Yeah, when you have growth, you also have death, right? So rate of cell death, during the course of fermentation, a significant number of cells might die or deactivated during the course of fermentation. The rate of expression to describe this can be written as, this is nothing. Everybody can come up with this. I think I've explained to you. I taught you guys in the Malthusian model. Rate, right, is always proportional. When you talk about growth, it's proportional with the cell. It's the same with death. Rate of death is proportional with the number of cell concentration. The higher the cell concentration, the higher the death rate, right? So with that, you can just turn it into this equal sign, and then therefore you have a constant here, KD. So KD is coefficient for cell death rate, right? So the unit is per hour, correct, right? Why the unit is per hour? You can check yourself, right? For mu is also per hour, right? So you can check the unit, make sure all the units are correct, all right? So rate of cell death, that's basically the end for our kinetic models for growth, right? So next, we move to a new slide, which is on the yield coefficient and kinetics parameters in the substrate utilization and product formations. So moving to the next kinetic parameters known as yield coefficients. I hope by this point everybody is clear what is the difference between coefficient and what and constant, right? Coefficient is the, but again I try to explain here, coefficient is the numerical number that sits next to the variables, like y equal to mx plus c. M is the coefficients, all right? Constant is the one that stand alone. For example, y equal to mx plus c, constant is c is the constant, okay? So growth kinetic are generally further described by defining stoichiometrically related parameters. I think you understand what the word these words means, right? The number that relates between the reactant and the resulting species, right? Yield coefficients are defined based on the amount of consumption of a given material. Nothing, right? This is very simple. When you have a cell, you have, this is one of it, yield for biomass over substrate. So it's nothing. So it's a change in the biomass concentration divided with the change of substrate, right? Okay, it's actually like a slope of a curve, right? So the way to calculate it, you have the maximum cell concentration divided with the initial one. This one X naught, initial cell concentration. X naught is pronounced, this is actually equal to 0 at time 0 divided with the substrate concentration change. Right, this is very simple and straightforward. If you need to determine these kinetic parameters, very easy. Okay. Then you have this explanation. For growth limiting substrate, when culture nearing maximum cell concentration, when the cell concentration is nearing the maximum cell concentration, substrate is mostly spent, right? This is pretty clear, right? When it reaches the maximum, usually the substrate is mostly spent. No more substrate. That's why it also already reached maximum cell concentration. Hence, if plot maximum cell concentrations, again, initial substrate concentration. For example, we do several shake flask, and each of the shake flasks contain different substrate concentration, and then with the same cell initial inoculum, right, concentrations. If you try to plot this curve, then you should get a slope of yield X over S. You'll be like this, right? Say glucose, maybe you prepare a different shake flask, 1, 2, 3, 4, 5 different shake flasks, and in each of the shake flasks you have different substrate concentration, and therefore you obtain a different maximum cell concentration here, 1, 2, 3, 4, 5, and then you can plot this curve. The slope of this curve is equal to y over y yield X over S. All right. So what does this parameter means? I think you can see it from the relationship itself, because it represents the efficiency of converting substrate into cell. Okay. If you put P here, it means efficiency of converting substrate into product. So it's nothing, very clear. All right. Let us move to this. Okay. Even though biomass yield, okay, this is called biomass yield, can be determined as described, the value may not be constant throughout the growth curve. Okay, the value may not be constant throughout the growth curve. Why? This is mainly due to the consumption of substrate for maintenance requirements, right? Yeah, because in the real case scenario, the substrate is not only used for growth. The substrate is also being used for maintenance, and no growth occurred at that phase. So that's why there is a little bit of inaccuracy if you are using the previous methods, right? Okay. And therefore, Perth 1975 came up with a relationship between the effect of maintenance on the measured growth yield, right, in the form of these equations. So for this equation, you have this measured growth yield. So this is the one that you determine through experiment, all right? And mu you can calculate for each of the point, right? But now you have a theoretical growth yield, which is this, will be equal to the values that cross the y-axis, right? It's a c value actually. If you draw a comparison with y equal to mx plus c, and this one, the m, the slope is actually equal to the maintenance. Yeah, it's equal to the maintenance. All right. So maintenance coefficient m is usually very small and can be determined by plotting this as a function of 1 over mu, right? Because these are kinetic parameters, right? So you can't draw anything for curve. So you can only take this one as y, and then this one 1 over mu as your x-axis. Then you can get a slope to obtain the maintenance coefficients and the intercept 1 over yg. All right, this one is to calculate the true or theoretical growth yield. Okay. Determination of maintenance coefficient is usually made by using chemostat. Why? Chemostat is a continuous culture, right? Since it is difficult to vary mu in batch culture, all right? Because remember, in the continuous culture, you can play around with mu, because mu is related to the dilution rate, right? So let's move next. Okay. So the yield coefficient can also be defined for other substrate or for product formations, right? You can have P as well. Just now is biomass coefficient, right? You can also have P over S, this one for product. Depending on, usually people determine this P the X, right? And also another one is P over X also, right? There's also, instead of substrate, the oxygens, instead of soluble substrate, you can also use oxygen here, right? So there's even some range for yeast and bacteria, for this, which could be useful if you want to do for comparisons, right? I mean, comparison between your own experiment data and also the data that is published earlier, so that you can, you can improve, whether you are good, your system is good enough or not. Okay, so yield coefficients, yeah. Next, we move to this, all right? This is, all right, this is now on the substrate utilization, okay? Mass balance for determining substrate utilization rate, okay? All right, so do not panic, guys. My expectation is everybody can come up with this easily. All right, you don't have to memorize this, but you can draw this if you understand the idea, and I will explain to you. Okay, this is very easy diagram. Everybody can draw this, right? Inflowing feed, right? There should be a subscript I here, which stands for inflowing, right? This one is outflowing, right? You have the volume in the bioreactor, the X, S, and P, all right? So if you try to come up with a mathematical model for substrate accumulation rate in the bioreactor, so this is how you do it, okay? So if you look at this is basically the idea. Substrate accumulation. All this is basically rate, substrate accumulation. Why rate? Because of dx over dt, right? This one is actually rate, substrate accumulation rate, right? Substrate accumulation rate is equal to the substrate that you put in minus substrate that you remove and minus substrate that consume. This tree is substrate consumed by the strains, microorganisms or whatever, right? And then the substrate that is being consumed can be divided into three. You have the one that consumed for growth. You have the one that is consumed for product formation or synthesis. You can have substrate that is consumed for maintenance. So substrate utilization or consumptions usually for these three purposes. All right, and therefore to be more accurate or specific, we incorporated this in the equations. All right, so how do we get this statement, or we call this conceptual model? All right, this is a conceptual model. How do we get this? The basis for coming up with this is actually based on the initial mass balance. Remember? The initial mass balance, the very, very general one. Accumulation, rate of accumulation is equal to rate of transport plus rate of conversion. So rate of accumulation here, all right? Rate of accumulation is equal to rate of transport. Transport means the one that you give in and the one that you remove. Plus rate of conversion. Conversion means in this case substrate is the one that you consume, right? So that's why it's negative, the one that you consume, all right? So can you see that relationship? Accumulation equal to bioconversions plus transport. And then you try to be more specific, you elaborate it into this. Okay, all right, I hope you are clear with that. Next, from this conceptual statement or model, you try to come up with mathematical model. Can you do that? Yes, of course. So how do we do that? Substrate accumulation, if you try to put it in mathematical form, is nothing but ds over dt, right? Rate of substrate accumulation in a bioreactor. So it's ds over dt, right? Okay. This one is rate of substrate fat, right? Rate of substrate fat, you just put F inflowing multiply with substrate inflowing divided with V. So the trick is, all right, you have to check the unit for this. And the unit for each of these fraction is similar to here. For example, here ds over dt is going to be a gram substrate per liter per hour, right? And this fraction should give you the same unit, all right? And you can try to relate when you have F times S, right? This is gram per liter, this one is liter or volume per minute, per hour, all right? Or over time, right? So what is it? Then you divide it with unit of volume. What will be the resulting unit, right? You can check the unit. So and then you can derive this easily. All right. So should be no problem for these and these because they are the same. But then this one, this is actually if you want to have another intermediate level before you come to this mathematical equation, you can have this as the RS, small r with a subscript S symbol, no? RS, rate of substrate utilization. This is equal to rate of substrate utilization, small r with S subscript, all right? You can have that. So if you try to expand it, you get this, okay? This is just look at here, consume for growth, therefore is a mu x. Mu x is a dx over dt, remember, rate of growth, right? If you have dx over dt, rate of growth divided with these coefficients, yield of a biomass, you get the same unit as this, right? For growth. It's not really difficult to remember. You just take note of the word of growth. Growth is dx over dt or equal to mu x, right? Divided with biomass yield. For product synthesis, so product, you have a new one, QP, all right? So why is that it is? Product synthesis dP over dt is equal to QPX, right? Why X? Right? If talk about growth rate, dx over dt, it is equal to mu x. But if for rate of product formation, it's going to be a sum constant divided with x, right? Why x? Because yeah, the amount of product being produced is still correlated with the amount of cell, right? So that's explain why dP over dt is equal to QP multiplied with x, right? Okay. So if people ask you what is the unit for mu, can you answer that? Of course, the answer is per hour. But what is the unit for QP, specific product formation rate? Is it still per hour? No, right? So what is the unit for QP? In order to calculate the unit for QP, you have to rearrange the equation and you can check, all right? dP over dt is equal to QP multiplied with x. So if you leave QP as a function, what would be the unit, right? You can check by yourself, right? So this is rate of product formation divided with product coefficient, right? If you're talking about growth, you have mu max. If you talk about product, you have QPX, all right? And then you just divide it with the coefficient. You can check whether the unit here is similar with this or not. It should be the same, all right? For maintenance, it's just mx. So the question is, what would be the unit for m, right? Yeah. Because here you have gram per liter, gram cell per liter, and here you have gram substrate per liter per hour. So what do you think the unit will be? M. M should contain per hour or over per time, right? It should also contains per gram, because you need to remove the per gram for this X, right? So the unit for this should be what? Gram substrate over gram cell per hour, right? That should be the unit for M. Okay, so let's check here. F inflowing feed, inflowing feed, outflowing feed. So flow rates of medium into and out of the bioreactor in a unit of liter per hour, volume over time, right? You have V, volume of culture. You can have liter here, it's a common one, right? Substrate, initial substrate concentration, inflowing substrate concentration, outflowing substrate concentrations, or substrate concentration at the outflowing region, outflowing fraction. You have QP. QP is this one. What is QP? You can just take note, look at this subscript. PP means product. So this whole means specific product formation rate. Is the unit correct? One per hour? So the answer is not correct. So this is not correct, right? So you can correct this, explain to you just now, right? For QP, the unit is not per hour, all right? This is only for growth, for mu, right? M, the maintenance coefficients, maybe you have a more complex unit because you want to make it similar with this part, right? And therefore you have this, okay? So it's not that difficult, right? To come up with these equations, isn't it? All right. So this is basically the ultimate form of the equation. You can have another intermediate one here, wherein for intermediate variable, you remember when you have type of variables, you have intermediate, you have a kinetic. So this one is actually the one that is already incorporated with kinetic parameters. And you can have in between of this, you can have another one with intermediate variables. For example, you can have here as an RS, as I explained to you. Okay. All right. And then we move to this. The general equation includes feeding of fresh substrate into the bioreactor, fed batch. All right. For batch culture, where there is no feed and substrate removal, the equation becomes, all right, so the equation now becomes simplified. All right, notice that the feed inlet and outlet have been cancelled. No more outflowing and no more inflowing. All right, okay. Why you have a negative sign here is because this is okay, to show or to indicate that the substrate concentration is declining. Therefore, you have this sign. Okay. All right. Since we are under the topic of yield coefficient and this parameter is related to substrate utilization rate, we therefore try to revise our substrate mass balance. Okay. Another one is that frequently the maintenance coefficient is very small compared with the term for cell growth for this fraction. As I explained earlier, when something is too small to something, for example, 10 to the power of -7, here you have 10 to the power of say -4. So this one is too small. You can neglect this, right? And then when there are no product formation, this fraction also, when you assume there is no product formation, you can remove this and you can remove this, and the equation becomes like this, right? So the question is when to actually remove and when to not. Actually, in real case scenario, it'll be better if you can determine all of this to incorporate all of these elements in the calculations, right? Yeah, because it will be more accurate and more representative of your system, all right? But if you want to make your calculation easier but less accurate, uh, you can also use this assumption, okay? All right, so then when just now we talk about QP, which is specific product formation rate, we also have specific substrate utilization rate or specific substrate consumption rate, QS, all right? Instead of P, you have QS. So S means substrate. So the unit is gram substrate per gram cell per hour, yeah? So you can see the difference, right? Between the three, you have mu, the unit is on just per hour, and then you have QP, and then you have QS, and their units are different, right? So you can determine QS, all right, by rearranging the previous equation. Just look at these equations, all right? Okay, so what is rate of substrate utilizations? The rate of substrate utilization, in simple terms, you can draw ds over dt, right? So ds over dt is equal to, is proportional with a cell concentration. So ds over dt is equal to a, a constant multiplied with x, right? This x is originally as at this place, at this on the left side of the equations, right? So if you want to have qs as a function, you take this x, put it here, okay? Right? Similar like the Malthusian concept. But now we are dealing with substrate concentration, right? So take note, this is not mu, it's now qs. And the unit is not per hour anymore, right? This is the unit, right? So if you want to determine that, okay, the same equation that you obtained previously, divided with x. And now the equation become like this. Okay. No more x as in the previous equation. Previous one we have x here, right? Right. So now no more x. So you have a new relationship that give you a relationship between this QS and also this yield coefficients. Yeah, the question is when to use this equation and what is the purpose of this equation. We'll see about that. Okay. Next, we have this microbial product. Okay. I think we have so far we have covered the cell growth, the kinetic models for cell growth, the kinetic model or parameters for the substrate utilization. And now we come to the third variables, which is product formations. So what are the kinetic parameters in product formations? All right, so we are going to look at that. All right, the first thing is when you have microbial products, you can describe the growth into three categories, right? The first one is called growth associated. It's nothing, you can just say the product is produced throughout the time. So if you plot a curve of X or P as a function of time, you get almost a similar trend, okay? So what it means is that product is being produced all the time, okay? Next, there's another one, which is, all right, before that, we have this as an example of the products, all right? Okay. Next, we have non-growth associated. Non-growth associated, you see that the product, if you plot a similar curve, the product is starting to be produced not at the growth phase, but at the stationary phase. It will be something like that. That's why it starts at this point. Okay. While another one is mix. Mix is like in between of the two. All right. So you can see the shape here. Mixed growth associated. So example of products, you can have all these examples as an examples. Yeah. Okay. So this is basically you can determine the categories of your product formations based on the shape of the shape or the trend of the curve. All right. This is a one way. What about the mathematics equations or models? All right, can we do that? Okay. This is basically the equations for product formations. Okay. So for product formations, similar, same, all based on the original generic mass balance equation, wherein you have accumulation equal to conversion plus transport. All right. Accumulation, product accumulation, dP over dt, transport, the one that is fed in, and the one that, no, I'm sorry, this is product synthesis, product removal, and product denaturations. All right. In this case, the element of transport is not being added. It's not being incorporated with the system. Right? You can actually add that to be more accurate for the general one. This one, product synthesis, product removal, and product denaturation. Oh yeah, you have for transport, only this is being added. All right, product removal, because you usually don't add product into the bioreactor, right? So you have only product here, right? Therefore, for the general equations, only the product removal rate is being added, okay? So this is part of the transport. And for these two, this is basically conversion, all right? So, you produce, and of course the product may also degrade or denatured, right? In the case of proteins, maybe protein-based product. So the equation now become this, all right? And product synthesis, rate of product synthesis, or in a short form, RP, all right? And product denaturation, you can have RD or RPD, more accurate, RPD. So you can have like intermediate equation here before you come to this, similar as the one in a substrate utilization. You can have dP over dt equal to RP, right? Minus product removal minus RPD, okay? So if you put to expand that equation, you get this, all right? You can check whether they are correct or not, because this is not correct actually. Can you find any problem with this equation? The answer is the one for product removal is not correct. right? Because you don't have element of product here at all. So it should be F outflowing multiply with P outflowing here, divided with volume. All right, so please take note on that. All right, and this is explanation on the variables. You have product concentration, rate of product decay for this, and specific product formation rate for QP, right? Okay. If product is stable and not removed from bioreactor, if product is stable, meaning no denaturation, this one you can remove, and not removed from bioreactor, and this fraction also can be removed. The equation will just be like this: dp over dt, rate of product accumulation is equal to rate of product synthesis, qpx, right? Okay. uh, And then if you need to determine this QP rearrangement to make it as a function, then therefore you have this. All right. So, all right. I think I've highlighted the answer. This is the fraction that is not correct. Okay. All right. That is basically a general equations for the rate of accumulation of product in a bioreactor. All right. So now is the one for determinations of kinetic parameters in product formations. So for this, you have an equations called Ludeking-Piret. Okay. So this equation basically is a more accurate way to determine the categories of your product formations, whether it is mixed growth, growth associated, or non-growth associated. Okay. All right. Beside this method, what are the methods? What is the method? What is the other methods that you can use to differentiate the categories? I've explained this earlier, right? Based on the drawing of the curve, right? Looking at the trend, all right. All right. For this, I think this one is also very easy. You don't have to memorize, but you just need to understand. Okay. Okay. One thing, the kinetic parameters for Ludeking-Piret is basically the alpha and beta coefficients. So what are these? Coefficient represent the growth and non-growth associated terms respectively, right? You can compare the value of alpha and beta with a previous experiment or previous literature. Also similar like in the case of KS and all that. Whether your system is good, your system is not good. So it's based on the comparison with the previous literature, right? They usually provided a range on that. So let's look at the equation. This one is very easy. You don't have to memorize, okay? When talk about rate of product formation, the mathematical equation is always dP over dt, all right? If let's say the rate of product formation is related to growth, right? Growth is dx over dt, right? In the form of mathematical form. So if let's say it's growth associated, it will just be proportional to dx over dt. And if you change the sign from proportional sign to equal sign, you have got a constant here. And the constant is alpha. So rate of product formation is proportional to the rate of cell growth, right? And alpha is just a constant, like in the case of mu, QP, and QS. All right. What about if the product is non-growth associated? Instead of dx over dt, it now becomes an x. Why x? As I explained to you, generally, whatever it is, remember in the concept of the autocatalytic reaction as well in the linear order, the first order, right? You can have like DPO, rate of product formation, is proportional with the cell. Whatever it is, the substrate, including substrate, is always proportional with the number of the cell presence. And therefore, dP over dt is proportional to x. And then when you change to equal signs, you get a constant here. The constant is named beta, right? Although it's non-growth associated, there is still element of X here. Why? Because everything is based on the cell concentration or the cell number. All right. For mix is nothing. You just add these two uh, element together. Okay. All right. Now you have this Ludeking period, a more general expression, right? What about if we extend this equation to include a kinetic parameters? All right. For example, when you have dx over dt, you can extend it to mu x because mu is kinetic parameters. So you kind of performing extension to these equations. It's the same with this and the rest. So let's have a look. So growth associated, right? Instead of dx over dt, now the equation become mu x, right? What's the idea? Why would we do need to extend these equations? We try to come to that later, all right? And this is for growth associated. When you extend that equation, you have this form, all right? And then you have partially growth associated. The partially growth associated, if you look at this, all right, now this is original one, it is being converted to C. How do you do that? Nothing but just divide it with X. When you divide it with X here, dt over dt divided with X, it becomes a specific product formation, QP. This one, alpha dx over dt, you divide it with X. dx over dt multiply with 1 over X, it becomes mu, right? And now you have a kinetics parameters. And then this one, you just leave it as a beta. You see, from this form, Ludeking period for mixed growth or partial growth associated, now you have a form in the form of C. Why C? Because you want something with a kinetic parameters instead of intermediate variables. Okay. All right. Next is, you can also see this relationship, and you will notice that it's actually in the form of y equal to mx plus c. So meaning that you can somehow you can determine the value of this by plotting that linear curve, right? Isn't it? So, okay, this is explanation on the catabolic reaction. All right. So this is explaining on the rate of accumulations of substrate in the bioreactor. All right. Uh, no, actually, it's the rate of substrate utilization by the cell. All right. Remember, when the rate of substrate utilizations, substrate is being utilized for growth, for maintenance, and another one for product formation, right? But now in D, you only see these two, and the product is being removed, right? Why? So these are the story. When the product is associated with energy metabolism as a catabolite of carbon source, right? When the product is associated with energy metabolism as a catabolite of carbon source, generally means the product is being used as a substrate again. Or in other words, if product is formed during growth phase, it may not be possible to separate out the amount of substrate consumed for cell growth from that consumed to produce product. Under these circumstances, all substrate consumed for growth and product is lumped into a single stoichiometric yield coefficient, which is the biomass coefficient. So that's why you only include these biomass coefficients. Why this arrangement is made? Why? we will have a look on this. Okay. So if you have D now, I mean the substrate utilization, okay, and this one is divided with X, you have a new form of this, right? And with this, we know that this one is equal to QS, right? And then we can replace the QS into the equations, okay? I hope everybody is quite clear with this already, right? This is nothing but just rate of substrate utilization is proportional with this X here. And then when you want to have this as a function, you bring the X from the right to the left, then therefore you have this. And this one is stand for specific substrate utilization rate, right? So you multiply the previous equation with these product coefficients, the equation become F, right? Okay, please have a look on this, all right? Explore on your own, okay? And then when you have this form, all right, this form, equation F, and then you know that this such a complex variables is actually equal to QP, all right? The equation can be rearranged into this, all right? Why we are working so hard to get this form of equation is because we want to draw a comparison with equation C. Equation C is also equal to Q is also is a function of QP. QP is equal to alpha mu plus beta. This is the one for mixed growth, right? Or partially growth associated. So the idea is to relate this substrate utilization mass balance equation with this Ludeking Piret. So why we are doing this? Because we want to kind of relates what is alpha and beta. You know, so this relationship basically give you an idea that alpha is equal to this, while beta is equal to this. Okay. All right. So this is the explanation sentence which explained my words just now. And the last one is a growth associated product. All right. So for growth associated, non-growth associated product, it's commonly for secondary metabolites, which are products not necessary for the growth of the organism, such as antibiotics and certain microbial toxins. So if you want to produce antibiotic, you expect to isolate the product during the stationary phase, right? So it is not possible in such cases to relate product formations and growth. So that's all. All right, for this, right? So I think maybe it can be a little bit of challenging here, but you need to understand the whole idea and concept. All right, so far we have covered the kinetic models for cell growth, right? In the kinetic model for cell growth, we have the three models, which is the Malthusian, logistic or Verhouse, and also Monod, right? And for each of the uh, growth kinetic models, they are also the graphical models, which is used to calculate the kinetic parameters. You can plot a curve y equal to mx plus c. For Malthusian is the one based on the ln x. Remember, ln x as a function of t. While we don't have one for the Verhouse one because it can be a bit complicated. And for the monod, we have presented three, which is the Lineweaver-Berg plot, Eddie-Hofstee, and also another one is called, I can't remember what's the name. Yeah, there's another one. Yeah, maybe you can check later. All right. I can't remember for now. And then we move to the substrate one. The substrate one, we talk about the general accumulation of substrate in the bioreactor, and then we specifically touch on the rate of substrate utilization, wherein it is divided into three: the one that used for growth, for maintenance, and also for product formations. And then we talk about uh, product formations, the category for the Ludiking period: growth associated, non-growth associated, and mixed growth or partially growth associated. In this, we did a bit on the mathematic equations, all right, the simple one. And then what we do, we try to expand the generic form of this mathematical equation, which consists of intermediate variables, to the one with kinetic parameters, all right. Yeah, so for Ludeking period, the most important kinetic parameters is the value of alpha and beta. Okay. All right. So this is the one for Monod just now. We have line weaver, we have Eddie Hofstee, and the third one, yeah, is Haynes Wolf plot, right? So guys, you need to explore on all these equations. Yeah, use a piece of paper and try to draw and derive all these equation by your own. So I expect all of you can draw these equations. You have to basically understand it rather than memorize. So yeah, with that you need a lot of practice on the derivation and the meaning and all that. All right. And of course, you also have the practical sessions uh, to actually learn how to use uh, the graphical model to find out the kinetic parameters, right? So I think that's all from me now, right? Feel free to drop any questions in the uh, forum platform, right? So till we meet again. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Bye.